All right, so today's lecture is a continuation of last lecture in our discussion of bending of beams, and also just for free, we've added in our discussion of plates as well. And really the goal was to give you this connection that beams and plates, they're not really so different in the end. And we can go through our analysis of beams at the same time as we go through our analysis of plates and establish all these interesting kinematic relationships. And they all come from fundamentally making certain assumptions about the kinematics, or how the bending deformations of beams or plates are simplified in some sense compared to the fully general theory of elasticity, which assumed that the displacement field, all three components of the displacements of some kind of solid body, are independent fields that we have to solve for. And we have all these different equations that we have to try to determine uniquely what are, the resulting strains that yield compatible deformation fields, what are the resulting stresses, respecting our constitutive law, and what are the resulting governing equations of equilibrium. And we simplified some of those kinematic assumptions, at least for the purpose of beam theory and plate theory, by imposing certain restrictions on how we assumed that these beams or plates deformed under transverse loading. And we invoked several common assumptions that I'm sure many of you were previously familiar with, pertinent to Euler-Bernoulli beam theory, the assumption that plane sections remain planar and perpendicular to the centroidal axis of some beam after deformation. And in the case of plates, there was a very analogous kinematic simplification, this idea of looking at individual fibers through the thickness of a plate. And we said that the kinematic assumptions in analog to beam bending were that straight fibers through the thickness of a plate after deformation will remain straight and will also remain perpendicular to the mid-surface of the deformed plate. So a lot of parallels, a lot of analogs between beam bending and plate bending and the resulting theories that manifest from those two different things. And I want to just recall some of the things that we looked at in the context of idealizing these beam and plate theories, simplifications of the more general theory of elasticity. We looked primarily at, if we're really only concerned about deformations of beams and the cross-sectional deformations are really not so relevant, then it suffices to just look at what's the deformation of, let's say, the centroidal axis or the neutral fiber of some beam, and we can parameterize that in terms of some axial coordinate x, and we can represent its transverse displacements in these two transverse directions, y or z, as a function of axial position x. In the case of plates, all we had was this transverse deflection in the z direction, but which varied potentially as a function of the in-plane coordinates of the plate as functions of x and y. So really what these functions represent are deformations or deflections of the midline or the centroidal axis of this beam and the mid-surface of this plate. Not necessarily saying anything about, what are differential displacements of points, on the top surface or bottom surface. Really, when we're characterizing relatively thin beams or plates, we can just isolate attention to what's happening to the neutral fiber or the mid-surface of a plate. From those descriptions of what's happening to the neutral fiber or to the mid-surface of these plates, we could describe what that deformation looks like, maybe in profile, and we could characterize different aspects of how these transverse deflection fields varied as a function of either axial coordinate or in-plane coordinate. We could take derivatives of these quantities to compute things like what's the slope of this, deformed neutral fiber of this beam, or what's the slope in maybe both the x and y directions of this deformed kind of section of the plate under, these kind of different forms of transverse deflection. And we could also look at what's the resulting curvature of these small sections or segments of a beam and plate under these different loads. So we could define things like, overall inclination or slope. We could then relate that to the resulting curvature in these beams. And we could define them basically as derivatives of these transverse deflection fields. And principally, we invoked this assumption of plane sections remain perpendicular to the neutral fiber in the case of Euler-Bernoulli beam theory in order to relate the resulting rotation of a given section to this kind of transverse deflection field. And we invoked that assumption, we enforced that assumption by basically insisting that transverse shear deformations that might occur internal to this beam are relatively small. And in that way, we were able to relate the rotation of a given section or the rotation of a given fiber in a plate to the resulting slope or inclination of this beam or plate. And once we had those relationships, we could go one step further and finally establish our final kinematic relationships linking the resulting curvature of a given beam or curvature of a given plate that involves now 3 different curvature quantities. We could relate curvature now to how does strain vary through the depth of a given beam or plate. In the case of beams, we noticed that the axial strain in any given fiber measured using some kind of relative distance from this neutral axis, we could measure what's the strain in this fiber given its coordinates, and it can be expressed as basically a linear function that depends on the curvature. Both values of curvature in bending due to displacement in either of the 2 transverse directions. In the case of plates, we found that it wasn't just axial strain that we were interested in, but rather we were looking at this more general case where we might have, let's say, a small chunk of this plate. We can cut out of it some kind of cube, and we can look at any particular slice of interest through the depth of this cube. And we noticed that really on a particular slice, that slice will undergo some kind of in-plane strains, axial strain in the x direction, axial strain in y, and maybe also some shear strain. And that state of shear strain will vary linearly as a function of depth z through the thickness of the plate. So in analog also to beam theory, that there's this assumed linear variation of axial strain through the depth of the beam, so too do we have linear variation of these in-plane strains as a function of depth z through the plate. So we've established all the kinematics by assuming, again, these simplified descriptions of plane sections remaining planar and perpendicular to the neutral axis, and straight fibers remain straight and perpendicular to the mid-surface after deformation for a plate. So those simplifying assumptions really enable all these things, but they only apply when you have relatively thin plates. They only apply when you have relatively small deflections of these plates. And they also only apply if the orientation or the configuration of these beams or plates are basically flat or initially straight. So there are some limitations, clearly, but it still applies for a wide range of problems of practical interest for engineering. So we've talked about all the kinematics. We've established some of the limitations and when it starts to break down, when it's no longer appropriate to apply these theories. But now that we have strain, as we did in our previous discussion, once we have some description of, simplified representations of deformation, we have a strain displacement relationship linking those kind of deformed displacements or transverse deflections of beams and plates to now the internal states of strain, but not all the components of strain. I want to point out that, these descriptions of axial strain in a given fiber, in-plane strain in a given slice through the thickness of a plate, that these descriptions of strain are incomplete. This only tells me one value of the axial strain in one of these fibers, but what about the other components of strain? We've already kind of assumed a couple of them. When we enforce this condition that plane sections have to remain perpendicular to the neutral fiber, implicitly what we were saying is that the shear strain, the transverse shear strain in a beam or a plate is roughly or approximately equal to 0. Not exactly equal to 0, it's just approximately 0, such that we don't really care about how that influences the overall or observed bending deformations under applied loads. It doesn't mean that it's 0, though. That's an important distinction. But what about the other components of strain, as is in the case of, like, let's say, a beam? What about, I don't know, the strain through the depth, the ZZ strain, or the YY strain in a beam? Are those necessarily zero? Take a guess. What do you think? Well, who's to say? Who's to say at this point? Well, I will invite you to consider one kind of thing that I want to point out is that at least if we're considering plates or beams to which we're assigning maybe no kind of transverse loads. So maybe there's some loads applied maybe far off on the end of this beam or on the edge of this plate, but along the length, let's suppose that there's no kind of external loads maybe applied to the top or bottom surfaces of this beam. So in some sense, if we wanted to characterize what's the ZZ stress, let's say, through the depth of this beam or through the depth of this plate, if I'm not applying any kind of external ZZ stresses on the top or bottom surfaces, then I think it's reasonable to assume that there is no ZZ stress, not on the surfaces, or really if the beam is thin enough, there's really no ZZ stress, through the depth of the beam. Similarly, we can argue that there shouldn't be any ZZ stress through the depth of this plate either. So what that means is we can say ZZ stress through the depth of this beam, through the depth of this plate, analogously YY stress through the depth of this beam into the plane of the page, that those quantities should be zero. But does that imply anything about what the resulting ZZ strain should be, either through the depth of the plate or through the depth of the beam? Not necessarily, yeah. We can't necessarily say that it's, that it enforces a condition that the ZZ strain is necessarily zero. And I want to distinguish this. If you're saying that I'm imposing some kind of constraint, I'm imposing a boundary condition, I'm saying that ZZ stress is zero. If I'm imposing a constraint on a stress-like quantity, I cannot also impose kind of the same kind of constraint on its corresponding kinematic variable. So if I'm imposing the condition that ZZ stress is zero, I can't really say anything about what ZZ strain is. In order to figure that out, I actually need to invoke my constitutive law. So in order to relate in a consistent way, what are the corresponding or resulting strains and stresses that should develop, let's say, in a beam or in a plate? I have to use that kind of general constitutive relationship that relates all of my components of strain to all of my components of stress. So in the case of a beam, things are relatively simple. I've said already that the transverse shear strains, they're not zero, but they're pretty small, at least compared to the axial strain. So I can say, well, they're pretty small. I can relate what the resulting transverse shear strains to the resulting transverse shear stresses. They'll also be pretty small, at least compared to the resulting axial stress in this beam, at least for any particular fiber of interest. But again, as I've said, if I'm claiming that I'm enforcing these boundary conditions, that the stress through the depth of this beam in either the Y direction or the Z direction are zero, equivalently, I might also say that I'm not applying any kind of like shear stresses on the top or side surfaces of this beam, at least shear stresses that act in a direction that lies in the plane of this cross section. Similarly, I could say that that in-plane shear stress applied to that external surface is also zero. So I have these kind of three conditions enforcing that the in-plane stresses that act, on the exterior surface of some cross-section imply that everywhere within that cross-section, also those in-plane stresses, I can reasonably assume are zero. But again, that doesn't necessarily mean those in-plane strains in the plane of that cross-section of a given beam, that those are necessarily zero everywhere. In order to enforce these conditions, to enforce these conditions, constraints on the stress, I have to invoke my constitutive law. So it is possible actually to determine what these resulting strains are. But for the purpose of doing our analysis, it's reasonable just to say that if I have these conditions, let's say that sigma yy equals 0 and sigma zz equals 0, those conditions nominally correspond to a state of uniaxial stress, where really the only resulting stress that should come out of whatever deformation occurs for a given fiber, the only stress of real significance or importance is the axial stress in the fiber. And the only way for us to come up with this relationship is to actually use our fully general three-dimensional constitutive law, relating all 6 components of strain to all 6 components of stress, but we've imposed a bunch of these extra boundary conditions on what these values of stress are assumed to be. Using those assumed values of stress, we can come up with what are the resulting values of strain that give me these corresponding values of stress. And given some known axial value of strain based on our assumed kinematics and how the beam deforms, we can finally come up with a simplified kinematic relationship between just axial strain and just axial stress. So effectively, we've reduced the constitutive law down to just this one-dimensional relationship, axial strain and axial stress. So it's almost like each individual fiber is behaving kind of like an independent uniaxial member. It's allowed to contract laterally, it's allowed to expand laterally potentially. But really the only thing that's controlling the resulting stress that occurs in that fiber is how much is it stretching out. It's sort of like you kind of say that, how fibers interact with each other, adjacent to one another isn't really so important. But it is important to know that at least the state of strain and stress in some kind of chunk of material in this beam is not so simple as just saying, well, it's just, only axial strain and only axial stress. Really, there are other strains and stresses that are occurring. It's just that we're really isolating attention to the strain and stress components that are relevant to that deformation. Similarly, for the case of plates, you can make similar arguments and say that I can enforce these different constraints on the stress field. Let's say the ZZ stress through the depth of this plate. I can also kind of enforce these approximate conditions that the transverse shear stresses through the depth of the plate should be approximately 0. And I can figure out then that there will be some kind of ZZ strain that might develop. It might vary through the thickness as a function of depth through the plate. But it basically allows each individual one of these planes to undergo a state of plane stress. And remember the conditions of plane stress. Plane stress implies that on a particular slice through the depth of this plate, on that slice, it will undergo some state of plane stress. It might have some in-plane stresses acting on it, some normal stresses or shear stresses in the plane of this kind of cut section through the depth of the plate. But I'm not confining anything. I'm not kind of imposing any, let's say, normal stresses on the top or bottom surfaces of this cut plane. So it's allowed to kind of shrink or maybe grow a little bit in terms of its thickness. And for the purpose of actually relating these in-plane stresses to the corresponding in-plane strains that we've determined from our kinematic or assumed kinematic relationships, really, we can just invoke our usual plane stress constitutive relationship. It's our reduced constitutive relationship relating these in-plane strains to the resulting plane stresses that occur for a particular slice through the depth of the plate. So in analog very much to the case of beams, we isolate attention really for a particular slice through the depth of the plate to just those stress and strain components of interest. But again, it doesn't necessarily imply that these other components of stress and strain are 0. They're doing more complicated things, but we're not saying anything about them. And they're not particularly relevant for governing what's happening in terms of the overall deformation of these beams or plates. Okay, so now that we have a relationship between strain and stress in both beams and plates, that's pretty useful. But we've kind of gone almost all the way. We need to bring it home. We've established our stress-strain relationships. We've established our kinematic relationships or our strain displacement relationships. The thing that we have to use to tie it all together is equilibrium, right? We've done compatibility, we've done the constitutive law, now we need equilibrium. But equilibrium, remember, Equilibrium was the statement of point-wise balance of forces on any kind of arbitrarily small chunk that we might choose to hack out of some larger body. The problem now that we encounter with these beam and plate theories is that it really doesn't do to try to just take a small chunk out of maybe one of these fibers and consider equilibrium on that fiber alone. We could try to do that, but again, we're kind of working with incomplete information here. If we don't really care about what these other components of strain or what these other components of stress are doing, then should we really even try or bother to enforce equilibrium on kind of these small subsections of a given cross-section or a given fiber? I mean, we could do it, but it would make the solution of these problems much more complicated. So instead, we actually take a page from the theory of finite elements and how finite elements actually go about discretizing problems and simplifying things, instead choosing to express equations of equilibrium, not in terms of point-wise statements of equilibrium. At every point on this cross-section, we have to satisfy equilibrium. No. Let's make it simpler. Let's say rather than trying to describe equilibrium in a point-wise sense over the cross-section, let's try to describe it in kind of a homogenized or a section-averaged kind of perspective of equilibrium. So rather than saying every point has to satisfy equilibrium, let's say that in an integral average sense, over the entire cross-section, can we maybe try to satisfy equilibrium in that kind of homogenized or average sense? So in order to do this, we have to take our resulting stress distribution, which might vary as a function of depth through a given beam or as a function of depth through a given plate, and we can compute what I'll call stress resultants. Stress resultants are really integrals of the stress, which varies as a function of depth through a given beam or some such. It's the integral of that stress multiplied by some other function. It doesn't really matter for the purpose of this analysis exactly what that function is. We could just make it a constant, in which case the integral of just a constant times the stress over the cross-section gives me the average stress over that cross-section. And in that sense, we could come up with statements of equilibrium that enforce equilibrium of the average stress over a given cross-section. In some sense, you've already done this, and you're probably well familiar with that concept of just trying to establish equilibrium relationships between these stress resultant quantities and just kind of blurring your vision and forgetting about the fact that really these stresses vary through the depth. If at the end of the day, all you really care about is equilibrium of the resultants, then the specifics and the details of how the stresses vary over the section and whether or not they satisfy equilibrium in a point-wise sense is kind of just like in the details. You can just kind of forget about it. Now, that's a little dangerous because obviously, what if we're violating something here? If we're just looking at equilibrium in this section average sense, looking at equilibrium of stress resultants, equally, instead of looking at the average stress over the section, I could multiply the stress by some, coordinate, y, measured relative to the neutral axis, and come up with the first moment of this kind of stress with respect to integration over the cross-section. Obviously, we call that moment in the classical sense, which characterizes something about the actual tendency for this section to want to kind of bend. And it would nominally correspond to, in a perfect world, an assumed linear distribution of the stress through the depth of this beam. It doesn't necessarily mean that the stress will vary linearly through the beam. It just means that maybe there's some more complicated variation of how the stresses evolve. And things can become more complicated if, let's say, you have a composite beam. If there's multiple materials that you're using to discretize this beam, then really, every time you kind of jump to some different subsection of this beam, the stress might actually jump a little bit. And there might be discontinuities in how exactly this stress varies through the depth of this section. However, if all we care about is the stress resultant, it doesn't really matter how this stress varies. We can define the moment still through this integral relationship. And we can kind of approximate the resulting variation as though it were kind of an equivalent linear variation through the depth. That's an important distinction, though, because oftentimes in engineering analysis, someone might come to you and say, well, here's the bending moment internal to this beam, and you might be tempted to say, oh, well, if I know the bending moment, then I know what the resulting distribution of stress should be through the depth of this beam. No. You can only assume that if the material remains homogeneous, if it doesn't change material properties, and a few other things. But really, the main one is just assuming that the material is homogeneous, that it's kind of one continuous material, and it doesn't change in terms of its elastic properties. In the more general case, though, this distribution of stress might not necessarily be linear. So that's just a caveat. Be aware of that. So when we define stress resultants, we can really only go this one direction with confidence. Going the other direction really requires some careful thought as to whether or not it makes sense to assume a linear distribution or variation in stress. In any case, we can do this. We can come up with stress resultants for a beam in the usual way. Just integrate some kind of linear coordinate, y or z, with respect to the axial stress over the entire cross section. And I can come up with different bending moments that might act in different orientations, depending on how they vary with respect to y and z. I can do the same thing in a relative sense for plates as well. But in that situation, it becomes a little bit more complicated. Now, there's plenty of new stress resultants, in particular, these kind of bending moments that you can integrate through the depth of some plate. They all vary as a function of z if we want to come up with what these bending moments are. But they have different values depending on, let's say, which of these different faces are you looking at on the exterior surface of this plate or something like that. And in general, you might have, yes, true bending moments that are kind of representative of the mxx or myy quantities. But interestingly, you might also get resultant torques as well. The mxy or myz resultant torques that act on this kind of different opposing faces of this hacked out chunk of a plate. Interestingly, though, these resultant torques, mxy and myx, happen to cancel each other out. They're equal to each other. And in some sense, that is a consequence of basically moment equilibrium, which you could enforce basically at almost like the material point level. Or if you like, you could just say that really in order to prevent this whole thing from spinning out of control, you kind of have to assume that these two things are equal to each other. So in any case, there's different ways that you can define this, different ways that you can come up with these stress resultants. And I'll also point out something interesting. In the case of stress resultants for beams, the resulting units for moment are stress times some unit of length integrated over some units of area. So force per unit area multiplied by kind of infinitesimal area gives me force multiplied by length, right? So the resulting units of these resultant stress quantities for moment are force times length, which makes sense. Force times a moment arm gives me some kind of moment. In the case of stress resultants, as I would compute for plates, it's important to distinguish that the integral that we carry out is not over one of these cut surfaces. It's not over an area necessarily. It's really actually just an integral over this fiber. It's a one-dimensional integral. So it's really just integration with respect to depth c. So that's an important distinction from how stress resultants are represented in beams as compared to plates. In the case of plates, it's units of stress multiplied by some infinitesimal unit of length and multiplied again by a length. So the resulting units of these stress resulting quantities for plates is not a force times a distance, but rather it's just force, which is a little confusing. But the way that I'm going to encourage you to think about this is not as a unit of force, but rather as a unit of moment per unit of width. So in some sense, these resultant stress quantities, you could think of them as the resultant moment that would act on this cross section but then divided by the apparent width of that cross section. So really, these resultant stress quantities are resultant moment per unit of width of this kind of small chunk of material. So one important thing to bear in mind, that especially if you're going and you're trying to use these different finite element analysis tools that implement plates, sometimes they'll spit out these resultant stress quantities for plates. And you might be tempted to look at those and say, well, this is the internal moment in this plate. But if they're reporting these particular resultant moment quantities, you have to be careful with the units. Is it truly moment internal to the plate, or is it moment per unit of width? That's something to watch out for. Just be careful that those things can kind of get you. All right. So now that we've established some description of how do we simplify the problem instead of looking at equilibrium of, let's say, individual points on a cross section or individual points along a given fiber, we've instead come up with these resultant stress quantities or resultant moments that might act on the cross section of a beam, or resultant moments per unit of width that might act on a particular fiber in a plate. And I can put all these different relationships together, all the preceding relationships that I just showed you. I can take my description of strain in terms of my bending curvature, which is basically, again, bending curvature comes precisely from the assumed deflected shape of these beams or plates. From curvature, I get strain. From strain, I get stress. And from stress, I get these stress resultant or kind of moment quantities integrated over each of these different things. And I can assemble all those different relationships together. Curvature to strain, strain to stress, stress back to stress resultant, and put them all into one combined statement to make things a little bit easier to swallow. And in the end, it looks hopefully a little bit familiar to you. In the case of beams, it looks something like this, that the resultant moment acting on a cross-section is equal to E, that kind of parameter that comes from our stress-strain relationship, I, which is the second moment of area of that particular cross-section of interest, and kappa, the curvature of this segment of a beam. So I have what I'll call the moment curvature relationship for a given beam. And it's a little bit complicated. I'll break it down exactly what I mean. You're probably used to seeing this in terms of scalar quantities, where m, moment, is really just one quantity. Kappa is also just one quantity. Same thing, moment of inertia or moment of area is also just one quantity. So if you wanted to, you could just express this as just one function. I'm actually representing this in terms of treating moment and curvature as potentially vectors that have two components, accounting for the fact that I might have displacements in either of the two transverse directions, in the y direction or the z direction. And similarly, I might have stress resultants bending about the y or z axes due to deflection in the y or z directions. And the relationship between these components of bending curvature in the y or z directions and bending moment due to those displacements in the y or z directions is not so simple as just saying, okay, well, bending moment y is somehow directly related to curvature y. Bending moment z is directly related to curvature z. It's actually a little bit more complicated than that. In general, this second moment of area term, I, is how I'm representing it, not to be confused with the identity tensor, is actually more appropriately idealized as kind of like a 2x2 matrix that has entries kind of like what I've shown here. So you might have an integral with respect to y squared on this upper left-hand portion, might have an integral with respect to z squared on that lower left-hand portion. But the thing that throws a wrench in our works is precisely this kind of off-diagonal term. Sometimes people call this the product of inertia. And the presence of this off-diagonal term in this 2x2 array representation of what I'll call the inertia tensor, the challenge that this introduces is that, technically speaking, curvature in the y and z directions can kind of get mixed up and result in kind of coupling between bending that might happen in the y or z directions and resultant moments that might develop about the y or z axes. That's something that might not have been well discussed in your previous coursework. If this is something that you have heard of, go ahead, raise your hand. Who has heard of this kind of like product of inertia term that shows up if you're dealing with, sometimes it's more appropriate to discuss it if you have, let's say, beams of non-symmetric cross-section. But in general, it can show up and cause this kind of interaction between bending moment in different directions, and specifically if you have biaxial bending. Who's actually heard of this concept before? Maybe, yes. Others, perhaps, or perhaps not. It's something that maybe you might have had time to discuss or cover in your strength of materials coursework prior to this. But in general, it really kind of upsets a lot of your previous thinking that like, okay, well, if I have, let's say, force on a beam that's acting in, let's say, we'll call this the y direction, then I should have bending moment that develops in that direction and resulting bending curvature that develops in that direction. But now I'm saying that it's not so simple. If I have, let's say, a force that acts in this direction, it might not just generate kind of bending curvature and bending moment in that same direction. It might also cause this beam to displace out of place and develop some kind of bending curvature in the opposite or kind of like mutually perpendicular direction, which is sort of a paradoxical result. But really, it has to do with the fact that if we have this more general description of this product of inertia term that relates, these different components of bending curvature to bending moment on a cross section, that coupling is kind of implied. It doesn't always show up though, and I'll explain a little bit later why or when we actually have to consider it. In the case of plates though, there's sort of an analogous description of this moment curvature relationship, but instead of involving just a scalar term for the linear elastic relationship between stress and strain, instead we plug in our kind of 2D plane stress constitutive matrix, which is this kind of 3x3 matrix that maps these kind of three components of curvature, the resulting three components of moment per unit width. And it also involves this kind of integral term, similar in nature to the second moment of area, but in this case, it's actually just an integral over, again, just a 1D line segment. So the interpretation of this I term is actually expressed in terms of units of length cubed rather than length to the fourth, as you would normally have it in a second moment of area calculation for a cross-section of a beam or something like that. All right, not particularly interesting to dive further into the subject of plates, though. I want to really go back to this idea of what's the deal with this product of inertia thing? And when do I actually have to worry about it? Well, I'll invite you to kind of consider it through the lens of a particular example that I think is hopefully illustrative enough. Suppose I wanted to compute for a given rectangular cross-section different components of this inertia tensor. Let's say we can define them as IZZ, or the moment of inertia as measured relative to the z-axis of some beam. Same thing, I could compute what's the y component of the second moment of inertia, which is defined kind of thusly as basically the integral of the cross-section of either y squared or z squared. These are things that you're probably familiar with, things that you've probably spent some time doing in the past. And we could do that. We could, actually carry out these integrals, or we happen to know for a rectangular cross-section, there are direct formulas for these particular shapes. We can just pull them out and say, okay, well, here are the quantities. I can do that either by integration or from the formulas, but what about the product of inertia? This kind of mixed term that's not y squared or z squared, it's y times z. In that case, it so happens that for cross-sections that happen to be symmetric relative to however you've chosen the axes, and assuming also that you're defining these measurements for the y or z distance relative to the centroid of this cross-section. So I'm careful about how I actually choose the coordinate frame in which I measure and compute these different quantities. It's always with respect to the centroid. But even if I do that, in the case of this kind of symmetric cross-section, a rectangular section, I find the product of inertia is just 0. So in that rather trivial case, I don't actually have to worry about it. I can just forget about it, which is probably why you've maybe never heard of this. Because actually, for a lot of cross sections that you would want to use in practice, the cross section is actually symmetric, usually with respect to some principal axes that you've chosen that happen to be also carefully aligned with the direction of loading. So if you think of any kind of like I-beam section, a circular section, a square hollow section, most of these different types of sections are symmetric. In which case, for all of those different types of sections, the product of inertia is just going to be equal to 0. So it's a good reason that you probably didn't dive into those topics. It's a little bit in the weeds. Even so, let's suppose that I had this same rectangular cross-section and I just rotated it a little bit, maybe by 45 degrees. And now I told you, with respect to this rotated configuration, what are the resulting components of this inertia tensor? Computing IYY, IZZ, and IYZ in kind of an integral sense with respect to this rotated frame. We could certainly do that. We wouldn't be able to use our nice formulas from the table anymore. We'd probably have to do some kind of parameterized integral over this thing to actually figure it out, but we could do it. When it comes to computing the product of inertia, though, now with respect to this rotated YZ coordinate frame, this cross-section is not symmetric. If I tried to mirror it about the z-axis, or if I tried to mirror it about the y-axis, it would look like a totally different section. And because of that lack of symmetry, we have a product of inertia that is non-zero. In general, if you have some kind of non-symmetric cross-section, at least with respect to the chosen axes like so, you will have some kind of non-zero product of inertia that you have to worry about. And it shows up again in this kind of representation of the second moment of area as expressed through this inertia tensor. So what do we do? How do we get around this problem? I mean, in some sense, is it really a problem if we've already established that really we're just expanding our perspective to say we can compute what are the bending curvatures, we can compute what these different components of this inertia tensor are, and we can relate the resulting components of bending moment expressed as a vector to the components of bending curvature, also expressed as a vector through this matrix vector relationship. Somewhat more general, it really complicates things when you try to invert this relationship. If, let's say, you're given bending moment and you want to go the opposite direction and kind of invert this relationship, determine what's the resulting bending curvature given the internal bending moment. To do that, you could certainly take this 2x2 matrix and invert it to come up with what's that reverse relationship. But it certainly makes doing things and solving typical bending problems a lot more cumbersome. So an alternative approach to circumventing this issue of what do you do when you encounter a cross-section that has a non-zero product of inertia, which happens commonly if you have non-symmetric cross-sections? Well, we can go back to way back, chapter 1, our discussion of how do we deal with tensors, and in particular, how do we deal with how these components of tensors change as we change our perspective, as we change our frame of reference. And this is particularly relevant for stresses, for strains in a two-dimensional setting, but it applies equally to this notion of inertia treated as this two-dimensional tensor quantity. I can take the components of my inertia tensor, originally represented with respect to maybe some particular chosen YZ coordinate frame. I can compute all of its different components. I can assemble them into this 2x2 array. And let's say even in the case of this example, maybe I find that it's much easier to compute, let's say, the components of this inertia tensor with respect to this coordinate frame. But I really want to know what are the components technically with respect to this coordinate frame. Could I somehow compute everything with respect to this frame and then just kind of take all those components and transform them or rotate them in some way to express them instead in terms of this different coordinate system? And the way that we do that is in the same way that we rotated stresses. If we had stresses defined on some block of stress, and we knew what are the different normal components of stress and shear stress acting on those faces of that block, but instead we wanted to know what are the resulting normal and stresses and shear stresses that act on a similar block, but in a different coordinate frame, shifting our perspective by some kind of rotated angle theta. in order to do that transformation, we can do basically or exactly the same transformation by taking that inertia tensor expressed as this 2x2 matrix and then left and right multiplying by some kind of rotation matrix, where this rotation matrix again has components that are expressed in terms of sines and cosines of that rotation angle theta. I won't go through the details of exactly how do you carry through all these, matrix multiplications to actually figure out what are the specific components of this rotated inertia tensor and how do they relate back to the components of the inertia tensor represented with respect to some original chosen coordinate frame. But you can go through the process. You can even just go into chapter 1 of your textbook, and it basically just used exactly the same formulas that you use to transform components of stresses from one coordinate frame into another. So that's one way you can get around this problem. It's convenient sometimes to compute the inertia tensor with respect to some kind of preferred or chosen axes, particularly symmetry axes, if the section exhibits some kind of symmetric behavior. But even in the most general case, where maybe there aren't specific axes of symmetry for a fairly general cross-section, as you might have, let's say, in the case of this kind of L angle section. This is particularly relevant for that homework problem. In this particular case, it so happens that irrespective of whether or not this section indeed even has a particular coordinate frame in which it exhibits symmetry about both reflections about the y or z axes, it actually doesn't matter. There is always some coordinate frame in which I can choose to rotate my inertia tensor by some, specially chosen angle theta. And it turns out that I can always find this coordinate frame in which I basically decouple these kind of products of inertia and end up with just a strictly diagonal representation for the inertia tensor. In that particular coordinate frame, you can think of these diagonal entries of this rotated inertia tensor as being kind of like equivalent to the principal stresses in some representation of a two-dimensional state of stress. In that context, they were representative of the strictly normal stresses that would act on some kind of block of material, assuming that the shear stress acting on the faces of this block in this rotated frame are equal to 0. In the case of the inertia tensor, it basically implies that the product of inertia is 0 relative to this specially chosen rotated frame. And the values that appear on the diagonal are sometimes called the principal moments of inertia. So these principal moments of inertia, you can use this formula to compute them, given some particular values of the product of inertia and the moments of inertia that are computed relative to some arbitrarily chosen coordinate frame, just for convenience maybe. But you can always find this special rotated frame in which this condition is satisfied. And really the benefit of doing this is that, let's say you wanted to solve this problem as presented in the homework. You had some beam, you had some kind of transverse loading that was nicely aligned with kind of the edges of this cross section and everything. But we recognize the fact that if we tried to solve this problem, we would actually have to acknowledge the fact that really, if we had loads that were acting, let's say, directly in the z direction, that's certainly going to generate deflections downward in the z direction, but it might also cause deflections laterally in the y direction, somewhat paradoxically. And again, that has to do with this coupling effect, that because this section is non-symmetric, because its resulting product of inertia relative to this coordinate frame is non-zero, deflecting this downwards and applying some vertical load will cause it to bend in this opposite direction. We could do that by, again, computing this relationship between, both components of bending curvature and both components of resultant moment through this general tensor relationship, or we could just treat it as a totally decoupled problem and instead choose to solve this same problem, not with respect to an original YZ coordinate frame, but instead with respect to this special coordinate frame, in which we basically said that there's no coupling between, out of plane deflections and kind of vertical deflections relative to this plane. It does mean, however, that we have to change the direction of loads such that it can be represented with respect to this rotated frame. But once I do that, I then only have to solve two independent two-dimensional problems. A problem that solves for what's the deflection in the z hat direction and what's the deflection in the y hat direction, given these kind of decomposed components of the applied load. Gets a little bit complicated, but you could certainly go through the exercise. And that's precisely what I've asked you to do in the homework assignment in order to come up with in the end, what's the vertical deflection in the z direction. But to figure that out, you do have to figure out what's first, decouple it into this kind of two different y hat and z hat problems, figure out what's the deflection in each of those two different directions, and then rotate it back into the original y and z coordinate frame to figure out then what's the vertical deflection with respect to that coordinate system. So a little bit of a tricky thing. It looks very deceptively simple, this problem. It's just like, oh, I have direct formulas. I can figure out what's the tip deflection of this cantilever beam just by going to some textbook. And I think what was it? It was like P times L fourth over 8EI or something like that. There's a direct formula that you could use to figure out what's the tip deflection, just given the assumptions that this is some, short beam, or rather sufficiently long beam. Assuming Euler-Bernoulli beam theory, you can figure out what the tip deflection is. That works for symmetric cross sections. For non-symmetric cross sections, obviously things become more complicated. So that's the one thing that I want you to be aware of. And the one thing that, will hopefully serve as a little bit of a nice challenge for the homework. So now that we've talked about how do we relate bending curvature to bending moment, the last step of all this is still to come up with expressions for equilibrium. We've reduced our descriptions of the state of stress over a cross section or through the depth of the plate, not in terms of pointwise statements of stress, but now instead in terms of these stress resultant quantities, in terms of bending moments. But to really go the full distance of enforcing equilibrium, we really have to describe equilibrium now in this kind of more holistic sense, taking equilibrium not necessarily relative to kind of a small chunk of material, but equilibrium with respect to maybe some kind of finite slice of a beam, considering all the forces that act on it, maybe any kind of transverse loading that might be applied to it, maybe whatever internal shear forces that might act on each of these cut faces of this cross section on the left and right hand sides, and whatever kind of internal resultant moment generated by, again, the relationships that we previously established. The challenge here is the fact that we don't really know what this resultant shear force is. We have a relationship between axial stress and the resultant moment that acts on a particular cross-section of a beam. But for the shear force, we've kind of fudged things in a way that doesn't really give us any immediate answer to what this should be. We've said that, well, if, let's say, we're assuming that shear deformations are small and resulting shear stresses are also small, then we basically said, well, this is just practically zero. That's not true, obviously. For this to be an equilibrium, there has to be some kind of shear force that would keep this whole kind of section of this beam in equilibrium. And really, the magic of this beam theory and plate theory is instead coming up with what this resultant shear force needs to be, such that we don't satisfy equilibrium in a pointwise sense. We actually come up with what it needs to be through application of this kind of global statement of equilibrium of a particular slice of this beam. So we can come up with really two equations in the case of a beam, at least in this kind of two-dimensional simplified view of things. We have sum of forces in the vertical direction. So whatever these shear forces are that act on the ends, and in combination with that, whatever this transverse load is, the sum of all these different force contributions have to sum up to zero. And then similarly, we can pose moment equilibrium. The sum of all the moments acting on this subsection of this beam also have to sum to zero. And we can express those, relationships, sum of forces in the vertical direction, sum of moments equal to zero on this little subsection. We can consider that expression for some beam of finite length delta x, let's say. And then we can also suppose what happens if we take that section of the beam and examine what happens as we shrink that section smaller and smaller. So as delta x becomes smaller and smaller, we actually find that in the limit, we come up with some interesting relationships, differential equations governing equilibrium, both shear force equilibrium and bending moment equilibrium. And in particular, bending moment equilibrium actually implies the following, that the shear force is determined directly from this kind of variation of the bending moment and how it varies with respect to axial coordinate. You can go through the derivation. I'm sure maybe you've even seen that derivation in the past, but the idea is this, that you have a differential relationship, that the derivative of this kind of internal resultant moment quantity with respect to axial coordinate precisely gives me the definition of this shear force term. And then summation of forces in the vertical direction basically gives me yet another differential relationship, this time relating the derivative of how the shear force varies with respect to axial coordinate. And in order to satisfy equilibrium kind of in a section-wise sense, for any point x along the length of this beam, I actually have to say that Q has to be equal to however V is changing with respect to x. So if there's a little bit of, let's say, transverse load Q, then really the difference between V on this side and V on that side is proportional to whatever amount of load that Q is supplying. So in other words, the change in V depends on how much transverse load we're applying. So V will increase if we're increasing the amount of transverse load along the length, and decrease if we're kind of applying the load in the opposite direction. You could do the same thing for plates. It's a little bit more complicated now because rather than considering just sum of forces in the vertical direction and sum of moments about a particular, like two-dimensional plane, now we have to do it in this kind of like planar configuration. So there's bending about the y-axis, bending about the x-axis, and sum of forces in the z direction. We could go through the same exercise. We could kind of shrink that kind of packed out block that might have delta y and delta x kind of finite length segments. See what happens if both delta x and delta y get shrunk to 0. In the end, we'll get similar expressions expressed in terms of these differential relationships between how these resultant moment quantities vary to find out what is the internal shear force acting on these different cut faces of, let's say, a small section of this plate that we've cut out. And then finally, we have our relationship between the transverse load applied to the surface of the plate and how that is related to the variation in the shear forces per unit width on these different faces of this kind of small section of this plate. So again, throughout this whole process, there's been direct analogs between how we idealize and how we come up with different equations relating, displacements to strains, to stresses, to resultant forces, and now equilibrium. They all have direct parallels. Obviously, it's a lot more complicated with plates. You have a lot of other things you have to worry about, but hopefully it gives you confidence that if you encounter plates in practice, they're really not so different from beams in the end. That's really the takeaway I want you to have, that as intimidating as they might seem, it's really just like you're doing an analysis for beams and you've extruded it out in an additional dimension. All right, so that's hopefully a good starting point for getting you on the way to completing the homework. Another thing that I want to highlight, if only briefly, is this notion of what do we do now that we know that technically speaking, there is some kind of internal shear force that acts on this cross section. Before we said, well, it's going to be small. It's going to be small. Don't worry about it. It'll be all right. We can forget about it for now. But we now know that really, if we can figure out what is this resultant moment, given all of our previous relationships, and now given this new relationship, we can figure out what is this shear force. Now the question becomes, well, given the shear force, what exactly is the distribution of shear stress that might act on a particular cross section? To figure that out, you actually have to go through a little bit of a complicated exercise. And again, it actually comes down to posing a statement of equilibrium to figure out exactly what is the shear stress that might act, not necessarily on an exterior face of this cross section, but we'll do something a little bit different. Suppose I have a small section of a beam placed in some kind of state of pure bending. So it has maybe some bending moments applied to, its ends, and they might not necessarily be perfectly balanced. Let's say they differ by a little bit, owing to the fact that this kind of section of the beam has some finite width delta x. All right, given this assumed homogeneous chunk of material for this beam, I could carefully go the opposite direction and say that if I happen to know, or somebody gave me what these bending moments were, I could kind of invert my relationship between bending moment and the resulting stress distribution in this cross-section and assume that it's just going to vary linearly through the depth. In that case, I can basically say that the axial stress distribution is going to vary as a function of, let's say, depth coordinate z relative to the neutral axis, and it'll look like mz divided by I. The familiar formula that you've probably seen before, probably heard a million times. Now, given this assumed linear distribution of stress through the depth of this beam, I can do something kind of fun. Rather than considering, again, equilibrium taken with respect to, vertical forces maybe applied on the edges, I could consider instead taking a small cut through this cross section of this beam. And instead of, maybe cutting it transverse to the beam, I actually cut it longitudinally. Kind of weird. So it's almost like I take this section of the beam and I can make any arbitrary cut through that section that I like and basically divide the section into two halves. Not perfect halves. Maybe there could be one side that's a little bigger than the other side, but it could have any arbitrary orientation through this section. But the idea is this, I can isolate one half of that cut section of this beam. Let's just say it's the bottom half. And from that cut half, I can say, let's pose equilibrium, not of some forces in the y direction, but some forces in the x direction now. I know that really, if I assume that the axial stress distribution varies linearly through the depth, then I can come up with what's the net force due to that assumed axial stress distribution through the depth on this left half. It might, be different from the resulting net axial force that acts on the right half. So there's a little bit of a difference there. And that difference is accounted for by virtue of some kind of shear stress that would have to act across this kind of longitudinal cut that we've made through this beam. Kind of weird. But this delta n, which I'll call basically the change in that axial force, owing to the fact that, again, these bending moments might not necessarily be exactly the same if they differ, and are applied at some relative distance delta x from one another, I can still say, let's pose equilibrium on this kind of section. So in other words, I'm saying that, delta n, whatever this kind of resultant force is, has to be proportional to the difference between these two loads. So delta n is precisely n at x plus delta x minus n at x. So fairly straightforward. I can also say that on one of these cross sections, I can compute exactly what this normal force is just by integrating this kind of variation of stress, assumed linear distribution, over this cross section, but not the whole cross section, just this kind of sub portion of it, which I'll call A star, the section of this cross section that belongs to this particular cut half of the overall section. So it's kind of a limited subset that lies everywhere, let's say, below this particular cut that we've made through the section. So if I integrate this axial stress distribution over this kind of A star subsection, I can come up with what is this net force that acts on that subset. And it turns out that I can express that rather simply just by kind of extracting things out, again, assuming a linear variation in the stress distribution, and I get something that looks like n is equal to mq over I, where q is really what I'll call this first moment of area integrated just over this A star subsection of the cross section. And then finally, we can do our nifty trick. We can say, really, if there is some kind of shear force that acts on this cross section, I could represent it as a total net shear force, or I could kind of reduce it down into something like an average shear stress that acts over this whole cut section. And I can obtain that quantity by basically just saying, let's take this net force, delta n, and divide it by the cross-sectional area of this kind of longitudinal cut. So in other words, delta n divided by delta x times the thickness or the width of the cross section. If I do that, I could also look at what happens as I shrink delta x down to 0. Because, I like limits, I like differential calculus and all these things, but it actually tells me something really interesting. I can take delta x, I can divide by t times delta x, the area of this cut section. I can take the limit as delta x shrinks to 0. And in the end, what I get is the familiar shear force formula that says that the average shear stress that acts over this entire kind of intermediate cut transverse through this section, that average shear stress is actually just equal to this VQ over IT, where V is precisely the shear force that we previously derived. So very nicely, we've now figured out a way of computing how does shear stress now vary on these different cut sections. And if we know how shear stress varies on this particular cut surface, then so too do we know what's the corresponding value of shear stress on kind of an equivalent block of material, noting that shear stress on this top face in the x direction has to balance with the resulting y component of shear force acting on this front-facing cut. So really, by the balance of those different components of shear traction, we can argue that really the shear force internal on this longitudinal cut at this elevation through the cut plane of this section is equal to really also the shear force that acts on the surface of this cross section at that particular elevation. So very nicely, we've come up with, without even having to worry about the particulars of how do we figure out all these relationships between strain and stress for shear strains and how they vary over the cross section, we've expressed it entirely in terms of equilibrium. Now, the one challenge that this introduces, particularly if you're looking at non-symmetric cross sections again, and again, this relates back to that particular homework problem that I gave you, the challenge that you'll encounter is that you could do this exercise of figuring out, maybe choose a particular chunk of this cross section, make an arbitrarily, chosen cut through it, and, look at equilibrium as posed on this kind of like subsection of the cross section. Based on this longitudinal cut, you can figure out then what's the shear force or shear stress that acts across this longitudinal cut, which is proportional exactly to the shear stress that acts on the face of the cross section at that cut point. And you could continue to do this, basically just continue to take different cuts and look at how does the shear stress vary as you continue to, choose different subsections of the cross section, going maybe along the full length of this thin kind of open walled cross section. In the case of a C channel, in the case of an L angle, you can do it in either way. But in the end, what you'll find is that the shear force or the shear stress, as it varies through these, different cut planes through the section, will vary basically as a function of parameterized distance S. If I choose to represent maybe, let's say, the linear distance where I make the cut S as basically a function of maybe position along this kind of flow in which these different shear arrows appear to be pointing, I can continue to look at, well, how does it vary as a function of S? And I can choose to represent the resulting distribution of shear force on the entire cross section through tau. I can basically parameterize it in terms of that S coordinate. And it looks basically like the formula we had previously, BQ over IT, but where Q, again, that kind of first moment of area of that kind of subsection of the cross section depends on this parameterized distance S that I'm choosing where I make the cut. Once I have that though, I can also figure out other interesting properties, like what's the resultant torque generated by this variation of the resulting shear force or shear stress as I move along this kind of distribution S. So if I integrate over this whole kind of section, the cross product of the moment arm with each particular, let's say, subsection of this kind of section, whatever its shear force is, I can sum up all the contributions to the net torque that would be generated on this cross section. And I find that in general, this torque generated by this kind of shear stress distribution might not necessarily be zero. So if I load up this cross section under transverse loading, if it's a non-symmetric cross section, I might actually find that in general, I might develop some torque, not just bending. It might actually start twisting the member as well. And in those cases, you can characterize that kind of behavior, this coupling between bending deformation and kind of torque, precisely by saying that really there should be some internal distribution of shear stress, and its variation over the cross-section may generate a torque. You can kind of be careful about where you actually choose to apply your transverse loads. And in particular, if you were to apply transverse loads at such a location that the resulting internal distribution of torque generated by that distribution of shear stress internal to the beam, if that happens to balance with whatever kind of like external torque is generated by applying the loads at some eccentric distance e away from, let's say, the centroid of the section, then it turns out that in that special case, you can actually cause these resultant torques to go away. You can kind of just say, in the special case, where if I choose to apply the loading at some offset or eccentric distance e, located at some position, sometimes referred to as the shear center of this cross-section, then I'll find that in that case, the torques will cancel each other out, and there shouldn't really be any twisting action that appears. To understand what happens when you do have some kind of resultant torque on the cross-section, we'll have to resume next lecture, where we'll talk about torque and torsion and all those fun things. But that's where we'll end it today. Hopefully we'll pick up and finish things off on Thursday. I'll see you then.